All right, page 237. We are on increasing, decreasing, real-world applications. All right, so these are common multiple choice questions, specifically when we get down to these tables here. But our goal is to draw a function, and I'll let you take 30 seconds to draw it, that's increasing at a constant rate. Draw a function that's increasing at a constant rate. Draw it, yep, just draw a function that's increasing at a constant rate. So when we say rate, we're thinking about the what? The slope. If the slope is constant, the slope should be all the same. So hopefully you're drawing just literally a line that is increasing. Now, I understand the font got goofy, kind of like it did on that test question. This is supposed to say F prime, and the other one's F double prime on all these. So if it's increasing, what do I know about F prime? Greater than 0, positive, yep. How about F double prime? Double prime describes its concavity. What would you say that, how would you describe this concavity? Doesn't exist. So I'm going to say there's 0 concavity or doesn't exist. I'm probably going to stick with 0. Same idea to the right. Draw a function that's decreasing at a constant rate, and then talk about, again, these are F prime and F double prime. Hopefully we just, again, have a straight line that is decreasing. What would we say about F prime then? Less than 0. And then again, F double prime equals 0. There is no concavity. It's not concave up or down. All right, so I would say those are fairly innocent, simple questions. All right, so now try to sketch something that's increasing at an increasing rate. So take 30 seconds, try to talk yourself through it. It's increasing at an increasing rate. When you say rate, you're thinking about the slope. So obviously it's increasing. It's not going to be a straight line. It either has to look concave up or concave down. So I'm going to argue that I think it should look like this, and then I'm going to put some slopes on there. What would you say this slope is close to down here? 0. Then maybe this has a slope of, I don't know, 1, 2, 3. Would you agree my slopes are getting bigger? The slopes are increasing. That's what this means. Okay, so it's increasing. F prime is greater than 0. Just that, not the second. Sorry. Yeah, I'll give you, I have to make something else. And F double prime is going to be greater than 0 because this is concave up. Okay. Let's jump to the one right below. Increasing at a decreasing rate. Increasing at a decreasing rate. So it still has to be increasing. So if this is increasing at an increasing rate, it's got to look going up, but it has to be concave down. And again, I'm going to put some slopes on there just to prove what I'm saying. If I think this slope is a slope of 3, then this slope is getting smaller, so it's 2, 1, and it's getting closer and closer to 0. So the slopes are getting smaller. So the slope is still positive, but F double prime is less than 0. It is concave down. So if you get stuck on these, really think about the numbers, and that should make it a lot more obvious. So I think the increasing ones are fairly simple. The decreasing, you gotta, again, I would think about the numbers. Try to draw decreasing at an increasing rate. And then put some numbers on it to prove it. Decreasing at an increasing rate. Are we going with concave up or concave down? Let's see. Let's put some numbers on it and see if we agree. At the top, what would you say this slope is close to? 0-ish. Now it's becoming, well, it's a negative slope. This is a -1, -2, -3. Is that increasing? No, I don't think that's right. I have to be decreasing, but my slopes have to get bigger. I think it's got to go like this. And again, think about the numbers. If this is a -4, then this is less steep, less steep, less steep, getting closer to 0. If you picture a number line, and here's 0, here's -4. If I increase, I have to get closer to 0 if I'm negative. I think it's got to look like this. So it's talking about the slopes increasing. So our f prime, if it's decreasing, is less than 0. And our f double prime is greater than 0. And our concave up. So the decreasing ones, like I said, are a little trickier. You're going to have to kind of draw them out for yourself. Decreasing at a decreasing rate. It's going to look like this. I want my slopes, again, I'm picturing a number line. I want my slopes to get smaller. So if this has a slope of 0, -1, -2, -3, -4, these slopes are getting smaller. They're getting more negative as I read left to right. So f prime is less than 0, and f double prime is less than 0. So the way the AP typically asks these questions is they'll give you a table similar to this, and again, I just threw 4 of them up here, but they're going to ask you to state whether f is increasing at an increasing rate, increasing at a decreasing rate, decreasing at a decreasing rate, or decreasing at an increasing rate. So very common multiple choice question. So I have a table of x and y values, so the first thing I'm going to do is go get these slopes. Okay? So I'm going to find the slope between these two values. So this is the 0.53 and the 0.76. Remember, slope is change in y over change in x. So I'm going to go y2 minus y1. So 6 minus 3 over 7 minus 5. So that's going to get me a 3 over 2. So I'm going to find each pair of slopes. So I'm going to get the next pair of slopes. Again, y2 minus y1. 11 minus 6 over 10 minus 7. That's going to get me 5/3. And then 16 minus 11 over 12 minus 10 is going to get me a 5 halves. Okay, so the first part's going to be super obvious. What type of f prime numbers did we get? Positive, so that tells me f is increasing. Okay, my slopes are positive. Now I want to compare my slopes. If I went from a 3 halves to a 5/3 to a 5 halves, 3 halves is like 1 and a half. 5/3 is 1 and 2/3, so 1.6 repeating. I'm sorry, 5/3. 5 halves is 2.5. What are my slopes doing? Increasing. So f is increasing at an increasing rate. So this means it's increasing, and the increasing rate tells me it's going to look concave up. These slopes are getting larger. Okay, so again, it was like a slope of 3 halves to a slope of 5/3 to a slope of 5 halves. My slopes are getting larger, so it should look concave up. Alright, so we're just going to do the same. We're going to practice all of these here. So let's find the next one. Let's find our slopes again. So I'll give you a second. Make sure you do y2 minus y1 over x2 minus x1. think I got a 3, 2, 1. Does that sound right? Okay, so my slope again is a what type of number? Positive. F prime is positive, therefore F is increasing. Now what are your slopes doing? Getting smaller. So it's increasing at a decreasing rate. Increasing at a decreasing rate. So again, that means I'm going up, but my slopes have to be getting smaller. They're getting closer to 0. So maybe that's a slope of 3, a slope of 2, a slope of 1. That tells me I'm concave down. I'll clear the next one in a minute. Is -5 halves, -2, -1 looking? Okay, so my slopes are negative, which tells me the function is decreasing. Okay, now the slope, so picture a number line. If you're at -5 halves to -2 to -1, did you actually get bigger or smaller? Bigger, right? This is -2 point, so like picture a number line. I'm at -2.5, then I went to -2, then I went to -1, here's 0. If I'm going to the right, I'm getting bigger. If I'm going to the left, I'm getting smaller. So this is decreasing at an increasing rate. Decreasing at an increasing rate. Okay, which means, so I'm decreasing. My rates have to be getting bigger, so they're going to start super negative, but then they have to get closer to 0. They're going to look something like this. So again, I had a -5 halves, then I went up to a -2, I went up to a -1. Be real careful with those negative numbers. And if you get stuck, kind of picture a number line and think about which direction you're going. Say that again? Yeah, on these, they don't do that to you. They're going to be real straightforward. They're just going to give you one section of that function, Dree. Is -1/3, -3 halves, -9/5 sound right? 9 halves? 9/5. Sorry. -9/5. Alright, so f prime is clearly a negative, so we know the function is decreasing. So again, picture a number line, here's 0. If I went from -1/3, and now this is more than -1, so I'm at -1/3, then I went to -1, then I went to something bigger than that. Clearly these are getting smaller, so this is decreasing at a decreasing rate. So visually, my rates have to be getting smaller, so I'm starting closer to 0, and they're getting more negative. So it should look something like this. All right. Now, we're going to use all this information to graph some functions out. So go ahead and flip the page. And this kind of just reviews that. I'm going to jump down to example 1. I understand it's a little blurry here, but we're going to try our best here. So this has appeared once or twice where they ask you to graph this function out. So we're going to get some practice with it. It says sketch the graph of the function having these characteristics. Okay, so the first thing I'm going to do is start with what I know just about the function. And I think I can plot a few points basically. I know at -4, my y value is 5. So I can plot -4, 5. I know at 0, my y value is 0. At 2, my y value is -3. And at 5, it's back to 0. Okay, so those are just the points. Now the first derivative tells us if our function is increasing or decreasing. Okay, so my function is going to increase. Let's look at our derivatives as well here. If the derivative doesn't exist, what is the function coming to? A sharp point. So I'm going to have a sharp point in here. Then eventually I have a slope of 0. So if I look at my sign chart, it went from a negative to a positive, which means I should create a what there? A relative min. Let's see, where my derivative doesn't exist, it went from a positive to a negative, which means it creates a relative max. So I'm kind of reading this as my sign chart. I'm looking to find my critical points when my derivative equals 0 and doesn't exist, and I'm looking at the sign changes. Okay, so I should have 1 max, and I should have 1 min. I want to keep that in mind. I should have 1 max and 1 min. This -4, 5 looks like the max, based off that point there. And the min was at 2, -3. This should be the min. All right, so not only do I have to pay attention to whether it's increasing or decreasing, the second derivative is going to describe my concavity. So as I draw this, when I'm less than -4, so kind of picture here's my line at -4, everything up until here, it has to be, the f value has to be positive, so it's to be sitting above the x-axis. It has to be increasing, and it has to look concave up. So draw something above the x-axis that's increasing, that looks concave up. Above the x-axis, that's decreasing. It has to increase. We are drawing function f. Go up. That's concave down. No. Check with your neighbor. Look at their picture. Are they increasing? Increasing. Does it look concave up? Come on, you can all do this. Increase. Gotta look concave up. Go. Increasing, concave up. Luke, that's beautiful. I got to say above the x-axis, and I've got to look concave up. So if the grader has to visually see that it's concave up, you can't have a straight line. It has to hold water. Now, we said the derivative doesn't exist, so we're anticipating a sharp point between -4 and 0. So from this section to this section, where's the graph going to sit? Above. What's it going to do? Decrease, and it has to look concave down. You got this. Stay above the x-axis, decrease, look concave down. God bless you. Above the x-axis, decrease. That is concave up. That is concave up. Concave down. Yes, you want to make sure you don't exist there at the top. Remember, got to come to a sharp point. Okay. So it should kind of look like a shark fin almost, right? It's got to make sure that this is a corner or cusp type looking thing. It should be a sharp point. The derivative does not exist. And really enhance it so the grader can see that if they have to guess, it's just wrong. No one's taking their time here. If they have to guess at it, they're not going to give you any credit. All right, between 0 and 2, where should the graph sit? Below, it should be decreasing and look concave up. So you're below, you're decreasing, and concave up. And it looks like this. I'm below, I'm decreasing, I can clearly say this section looks concave up. When I get to this point 2, notice the slope equals 0, right? So this should be a smooth connection here. Between 2 and 5, where's my graph going to sit? Below, it should be increasing and concave up. Below, increasing, and concave up. As far as being greater than 5, it needs to be above, increasing, and concave down. So above the x-axis, it's going to increase and look concave down. So something like this. We don't know what height it ends at, and that's fine. We just know it's above the x-axis, increasing, concave down. We got this? Let's see if it checks out. Point of inflection. Okay, so if I'm looking for a point of inflection, I'm looking when the second derivative equals 0 or doesn't exist. So here's a doesn't exist, here's a 0, here's a 0. Before -4, I go from a positive to a negative, so I should have a point of inflection at -4, which it does. It changes from concave up to concave down. At 0, we change from a negative to a positive. So at 0, I should change from concave down to concave up, and it does. At 5, it's positive to negative, so again, that should be another point of inflection. Concave up to concave down, so everything is checking out. All right, I'm going to give you this one. Take your time. Try to graph out, don't even read A, B, and C yet, just try to graph out what this picture shows. All right. Should be a sharp point, but something's goofy, something's still goofy. Well, it should naturally happen is what I'm trying to say. All right, between 0 and 1, where should my graph be sitting? Above the x-axis. It should be increasing and look concave down. So I'm just going to really stress that it's increasing and concave down. When I hit 1, I should have a slope of 0, right? So this should be like tangent. I should have a nice slope of 0 here. Between 1 and 2, I should be above the x-axis. I should be decreasing and concave down. Okay, so that works. That makes a nice slope of 0 there. At 2, my derivative doesn't exist, which means it has to naturally come to a sharp point. Okay? Between 1 and 2, I already answered that. Between 2 and 3, my function's negative, so it's sitting below. It's decreasing because it has a negative slope, and it needs to look concave down. That is how it naturally makes that sharp corner there. Oops, let me make that point a little bigger. Okay. And again, that should be very simple, so to speak there. Just watch those very carefully. It says, let f be a continuous function from 0 to 3. All right. State any relative extrema. Okay, now, I don't need the graph to answer that question. Okay, that's usually like a part C. Let's go back and talk about relative extrema. I have a max when who changes? F prime equals 0 or doesn't exist, and then f prime changes what? From where to where? Positive to negative. Positive to negative. So I'm going to start with just my justifying. F prime equals 0 or doesn't exist, and then f prime also has to change from positive to negative. So if I look at my f prime row, I circle where it's 0 or doesn't exist. At the 0, do the signs change from positive to a negative? Yes, so x equals 0 must be a max. At the 2, I change from a negative to a negative. Is that anything? No. Yep. Oh, son of a pup. I did mean x equals 1, sorry. X equals 1, yes. At the 2, I don't have a min or a max because f prime did not change signs. Okay, so I'm just going to put no min. Relative min. No relative min. All right, a point of inflection. How do we justify a point of inflection? First, it has to do what, though? Equal 0 or doesn't exist. And then f double prime has to change sign. So again, I don't need the graph to answer any of this. I'm just looking at the pre-made sign chart. So I'm going to look to see when the second derivative equals 0 or doesn't exist. So it equals 0 here, doesn't exist here. Equals 0 here. Does the second derivative change signs here? Well, can I say it changes signs here? No. Does it change signs here? It's negative to negative. So I'm going to say there are no points of inflection. Now visually, does that make sense? The entire graph is concave down, so that should make sense. There are 0 points of inflection. Nothing is changing signs. Okay. All right. Got a few minutes to kill here. We're going to go way back to the beginning. Page 5. Leo, this is for you. You have asked me for this. I got time now. Page 5. All right. So, let's get our chart in here. So the trig values we have to know are sine, cosine, and tangent. The 3 degrees from the table that we have to know are 30. Now let's put the radians in as well. That's pi over who? 6. 45 naturally comes next. That's pi over 4. And then 60, which is pi over 3. So when you get to a trig question on a test, if you have to draw this out so you're just visually looking at it, by all means, go ahead and do that. So if we need the sine of 30, we have to know the sine of 30 is 1/2. Who also has the same answer? Cosine of 60. Okay. How about the sine of 60? Root 3 over 2. Who is also the same as the cosine of 30. The sine and the cosine of 45 are both root 2 over 2. I always say, just as a silly little thing, I always say the tangent of 30 has all the 3's, which reminds me that it's root 3 over 3. Oh, has 3. Yeah, 30 degrees, all the 3's. I like it. Tangent of 60 is just root 3. And then the oddball, the tangent of 45 is 1. And that should make sense because remember, tangent is sine over cosine, and root 2 over root 2 is just 1. Okay? I feel like we're pretty good with the sine and cosine curves. Do I need to draw those out for anyone? We got that. Okay. Let's do this. Let's talk about kind of like the unit circle version here. So smack in the middle is what degree? 45/pi over 4. Before that is where I'd get 30, which is pi over 6. After my 45 is my 60, which is pi over 3. Okay, so as you move these around, it is always the degrees of separation with the x-axis. Okay, so if this angle is 30 degrees away in the first quadrant, then it's also 30 degrees away in the second quadrant. So if this is 180 degrees and I go 30 away, that's really 100 and 150. Now, everybody is a pi over 6. 5 pi over 6, because I'm picturing this to be 6 pi over 6 is equivalent to pi, which then is going to make that 5 pi over 6. 1 away. If I go 30 in this quadrant, so now I'm 30 bigger than 180, which makes that 210. That's how many pi over 6s. I want to be one more than this 6 pi over 6, so that makes this 7 pi over 6. Okay, in this quadrant, again, I'm just going 30 away, which degree-wise would make that a 330. So if this is 2 pi and it's over 6, that's really 12 pi over 6, which makes this 11 pi over 6. You can also say how many 30s are in 330. That gets you 11. Same idea. Okay, so when we're asked, we're just putting that same degree away if you're looking for the degrees, and you're comparing it to pi or to 2 pi. I'm going to do the 60s here. Well, we might as well do 45 since it's next. Sorry. Let's go 45. Okay, so smack in the middle is my 45. So I'm going 45 away from 180, which is a 135. Or how many pi over 4s? 3, because that would be 4 pi over 4. So that would make this 3 pi over 4. If I go 45 this way, that's 180 plus 45, or 225. If that's 4 pi over 4, that's going to make this 5 pi over 4. If I go 45 away from the 360, that's a 315. So remember, this is over 4. That's how many pi's over 4 to get 2 pi? 8, which is now going to make this a 7 pi over 4. Throw one more on here. We'll do our 60s. So this is going to make this a 160 from 180 is a 120. Now my denominator is an over 3. So that's 3 pi over 3. So that's going to make this a 2 pi over 3. 180 plus 60 would be a 240, which would be a 4 pi over 3, 1 greater. 60 away from 360 would be 300. So remember, this is over 3. That would be 6 pi over 3, which makes this 5 pi over 3. So when you're thinking radians. Okay, so again, they're just all multiples of each other. And we'll come back and do just more trig solving, but we're really just talking multiples. And just remind yourself, it's all students, tip, cows, and these are the positive trig quadrants. So trig, you're always going to get 2 answers. You'll be positive in 2 quadrants each time. Say that one more time. Correct. All right. Got a nice homework assignment. We'll start off with today. I wanted to give you 2 answers real quick that I didn't put on there just to make sure. Let's see. I don't have the answers at the bottom, but I just want to make sure you're good on this one. On number 6, I got 0 to the square root of 1/3, just so you don't get freaked out by those answers. For number 6. And number 7, I had 2/3 to 1 as my answer. I think the rest are super nice. These are 2 are great review again for the test on Tuesday, Test Tuesday. But just 6 questions there, and those are the 2 answers I got for that one, so you can compare.